Hey ANPers, this is Dr. Jones checking in. This is ANP1, Lecture Test 5, Video 14, wherein we cover page 15. So let's see if we can get this to record this time. All right, so let's go back a slide. So question, we'll cover that in a second. Okay, so this question. How does the action potential move down the axon? We keep saying that the action potential starts if the graded potentials are strong enough to bring the initial segment of the axon to threshold. That brings the initial segment of, that starts an action potential in the initial segment. So how does that propagate or sweep down the end of the axon? So there are two ways. One is continuous propagation. The role of the sodium-potassium exchange pump is to maintain homeostasis. Obviously, we're moving a lot of sodium and potassium, and we use the sodium ATPase pump to maintain homeostasis. Once we've moved enough ion that it affects homeostasis, we just pump it back where it needs to go. Okay, and propagation of action potentials. While graded potentials are purely localized events, action potentials propagate or spread down the entire length of the excitable membrane and do not lose strength with distance. Explain how this relates to sending a message down a very long movie line. Well, so back in the day before the Rona, we used to go to movies in movie theaters. And sometimes there was a line where you waited to get into the building. I know, right? So long ago. That's so long ago. Although I will say that my seats at the house are so much more comfortable than movie theater seats. I kind of like watching movies at home. Okay, so if you're waiting in line, and let's make it a socially distanced line because that just makes me more comfortable, because the Rona. And say the person comes out to tell you that they're going to unlock the doors, going to open the doors in 15 minutes, and then you can go into the movie theater. And they tell you to pass it on. So assuming this is not a game of telephone, and assuming that the message does not change, you or your group turns to the person or group behind you and you tell them the movie doors will open in 15 minutes, pass it on, and they tell the people behind them, 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 all the way down to the end of the movie line, and boom, everybody knows that the theater doors are going to open in 15 minutes. Again, assuming we're not playing telephone. With a graded potential, it'd be more like the person just yells, "We're going to open in 15 minutes, and if you're too far away to hear, then you just don't find out." So that's more of what a graded potential is. So, two ways. Continuous propagation, and this occurs in unmyelinated axons. In continuous propagation, you bring the initial segment of the axon to threshold, which starts an action potential, which we've drawn several times now. So that allows buku sodium ions into the cell up until peak. So many sodium ions have rushed into the cell that they now, you have a concentration gradient. You have a boatload of sodium ions here and no sodium ions here, or fewer. And so you have this diffusion called a local current that diffuses out in all directions. Well, you at plus 30 millivolts, you have brought so many sodium ions in that this diffusion actually brings the second segment of the axon to threshold, which starts an action potential in the second segment, which at peak brings in so many sodium ions that they diffuse around, and that local current brings the third segment of the axon to threshold. So each segment that is brought to threshold starts an action potential which allows so many sodium ions in that they diffuse around, and that local current of the sodium ion diffusion brings the next segment to threshold, which at peak has let so many sodium ions in that diffuse around in a local current that it brings the next segment to threshold. And that action potential lets in so many sodium ions that it brings the next segment to threshold, which starts an action potential, which brings the next segment to threshold, which starts an action potential, which brings the next segment to threshold, which is an action potential, which brings the next segment to threshold. And that's how the action potential propagates down the entire length of the sarcolemma, axolemma. Brr. Okay, so the kicker here is this only happens in excitable membranes, and if it weren't for these voltage-gated ion channels, none of this would be possible, right? So that's why voltage-gated ion channels are responsible for action potentials. Okay, so in continuous propagation, you one at a time activate every single segment of the axon with action potentials, and the action potential here starts the action potential here, starts the action potential here, and that's how you continuously propagate the action potential down every single segment of the axon. Some axons are very, very long, and continuous propagation is not very fast. So we also have saltatory propagation, because they're feeling salty. But it's funny. Okay, it was from like 5 whole years ago. It's still funny. Yes, it is. All right. Moving on. Okay, so saltatory propagation happens in myelinated axons. And what happens is the exact same thing, except the local current will bring the next node of Ranvier to threshold, which starts an action potential, which lets in so many ions. That local current brings the next node of Ranvier to threshold. So it's the same thing, but instead of bringing every single segment of the axon to threshold, it skips from node of Ranvier to node of Ranvier to node of Ranvier to node of Ranvier. Okay. So which is faster, continuous or saltatory? Saltatory is much faster because you're able to skip from node to node to node to node. In fact, if it weren't for saltatory propagation, if it weren't for the myelin sheath speeding up the movement of the action potentials, we wouldn't be coordinated enough to walk, because the axons from the motor neurons that move your legs and wiggle your toes are so long that without the myelination and the saltatory propagation, you wouldn't be coordinated enough to walk. So walking takes speed and coordination and strength, and it's a real privilege, those of us who are able to walk. And, you know, and that's the thing about privilege. If you have it, you can't see it. It's like when you're going along and you're perfectly healthy, and then like you get a cold or your allergies hit, and you like realize how good you felt, but you didn't realize at the time until you lose how good you felt. Yeah. That's how that works. Okay, so let's go over the last bit on page 15. And this is the chart. Again, normally I would have you all choose if we're going down or across, but, and again, this class is not a democracy, but when I don't care either way, I let y'all vote. So it's weird that I don't have y'all's input, but I've decided we're going across on this. So we're going to compare graded potentials to action potentials. Graded potentials can be either depolarizing or hyperpolarizing, and we drew that picture, right, to make that concept really hit. The depolarizing goes up, the hyperpolarizing goes down. Okay. Whereas action potentials, which we also drew, are only depolarizing. That when you hit threshold, it starts a rapid depolarization, only depolarization. Okay. Graded potentials, no threshold. No threshold. Depolarization, you have to hit threshold or nothing happens. Graded potential, you can change the result by changing the intensity of the stimulus. Like in our movie line, if the person yells, kind of says quietly, oh, the doors are going to open in 15 minutes, like only so many people are going to hear. But if they yell, hey, the doors are going to open in 15 minutes, then more people will hear. So the effect is changed based on the intensity of the stimulus. Action potentials are not. They're all or none. Either you send the message down the line or you don't send the message down the line, period. Graded potentials are passive. Action potentials are propagated. So each site depolarizes the adjacent, that means touching next to site. Graded potentials, the strength decreases with distance. Action potentials propagate. They're the same strength throughout across the distance. So there's no decrease in strength. Graded potentials don't have a refractory period, which we will talk about, that you can just keep zapping and you'll get a stronger result. We'll talk about summation in another video. And action potentials, there is a refractory period. I do want to say something else about that here in a second. And graded potentials occur in most plasma membranes, but again, action potentials only happen in excitable membranes that have voltage-gated ion channels, and that is the difference, the voltage-gated ion channels. So I do want to point out, especially in this continuous propagation, because we are diffusing backwards, what keeps the previous segment from reaction potentialing and the message from going backwards? And what keeps it from happening are the refractory periods. The absolute refractory period and the relative refractory period are an essential part of the physiology here, because they keep the message moving in one direction. Because even though those sodium ions diffuse backwards, because they just diffuse out in all directions, the previous segment is still in its refractory period. And so that's how we keep the message moving forward down the length of the axon to the axolemma. There are voltage-gated ion channels in the axolemma, in the membrane of the telodendria, and the membrane of the synaptic knobs. And the action potential at the synaptic knob is what causes the release of the neurotransmitter, the exocytosis of the neurotransmitter, and we'll talk more about that in another video, because that finishes page 15. So, Lord willing and the creek don't rise, this video will record, and we won't have this conversation again for a while until you watch this again. So thank you, as always, for tuning in. The education must go on. Dr. J out.